Okay, let's get started. Is it all good? Okay. Okay, we're going to continue. Well, there's still 30 seconds or so. Let's make sure this is working. It's working. Okay, we're going to continue the third week. Well, start the third week of this lecture. And remember that we were designing sequential logic and finite state machines. Today, we're going to finish sequential logic design. So you should be able to do both combinational logic and sequential logic. And then we're going to talk about hardware description language and Verilog. So this is what we covered in the last lecture, green stuff. All of the green stuff we've covered. Only the blue stuff is left. Oh, thank you. That's much better. So basically, we're going to design finite state machines today. We kind of designed them last time, but right now we're going to do it a little bit more rigorously, fully. But recall the first 10 slides or so, I'm going to jog your memory of what we covered. We talked about sequential circuits. Sequential circuits essentially produce output that's determined by current inputs as well as past values. These are circuits with memory. And we actually built a bunch of storage elements to make this thing work, right? And we had covered combinational circuits earlier. And this was my analogy for combinational versus sequential. And I think this really captures the memory aspect of a sequential circuit very well. The lock over here, the sequential lock on the right, to your right, has some memory. And we built a state machine for that sequential lock for a particular combination. And you can see the state machine. And we said that this is an asynchronous state machine because there's no clock in this case. There's no synchronizer, if you will. And you can verify the state machine yourself. And we discussed what a state machine is. State machine is really a pictorial representation of a discrete time model of a stateful system, essentially. And it has a finite number of states, finite number of inputs, finite number of outputs, and an explicit specification of how you can go from one state to another state, and an explicit specification of what determines each external output value and how it's produced and when it's produced. Does that make sense? So it's clear, hopefully. And this particular finite state machine has all of those characteristics, actually. And then we talked about how to build this. Basically, we need three elements, three circuit elements. One is the state register. We talked about that. This is how do you build the state register so that you can remember the current state that you're in. And then next state logic, how do you go from one state to another state? Next state logic determines that. And then output logic, how do you produce the output of the finite state machine given the inputs and the current state? And you can see that this is how you actually organize a finite state machine. Any finite state machine can look like this. I don't know what's happening. Anybody? There's some timeout that is present somewhere here, and that could be a finite state machine. There you go. A finite state machine is kicking in maybe some synchronous clock. Okay, but basically at the beginning of the clock cycle, next state is latched into the state register. And we actually spent some time to build the state register because what we started out with, the D latch or gated D latch, it was not enough, right? So we built the sequential circuits as well as the combinational circuits. So we said, remember that how do we implement the state register so that it has two properties? One is the data gets latched at the beginning of every clock cycle, and the data inside the state register is available for the full clock cycle, full duration of the clock cycle, so that the combinational logic for the next state logic as well as output logic can evaluate for the full clock cycle, and they can settle. And this is going to be very important for the timing lecture that we will start tomorrow. For now, ignore the timing. We want this desired behavior. How do we make it happen? We said that the latches that we designed until that point in time are not good enough because they're transparent. What does transparency mean? Transparency means that whenever the input value changes while the clock is high, the output value also changes. So this violates what we want to do. What we want to do is we want the input signal to affect the output signal only at the clock edge, right? And be available for full cycle. And then we develop the D flip-flop. So hopefully you can see that state changes on a clock edge here. Now this is really annoying. Some clock edge just happened, for example. Okay, well, maybe it'll keep you awake. Or maybe it'll keep you away from computers once in a while. Okay, I see a lot of people paying attention, so that's good. So basically, the state changes on a clock edge, and the data is available for a full cycle, because what we did was we actually had a, let's say, protector first latch behind earlier than the second latch. And this ensures that whenever the clock changes, when the clock is low, for example, the first latch propagates the value of D to the output of here. And whenever the clock changes from low to high, this is called the rising edge of the clock, the value of D that was propagated here gets propagated to Q because of the way clock is wired, as you can see, to the right enable signal of the first latch and the right enable signal of the second latch. Clock is basically, this is really annoying. You cannot see it, right? We need to fix this somehow. So when the clock is low, D goes here. When the clock is high, when it transitions to high, that capture D goes over here. Okay, so that's the D flip-flop. We actually covered this last time. I covered a little bit more because it's important. And we can actually use these D flip-flops to implement the state register, as many D flip-flops in parallel as you need, essentially. And I'll show you that in a little bit. But just to summarize, this was the last slide we covered in the last lecture. We say that flip-flop samples the input D on the rising edge of the clock or positive edge of the clock. You can easily design a negative edge triggered D flip-flop also, but this is a positive edge triggered D flip-flop. Yeah, and I think we said everything over here. So this is an edge triggered state element because it captures the data on the clock edge, as opposed to a latch, which is a level triggered state element, which captures data on a level. For example, when the clock is 1 or when the clock is 0, depending on how you tie the right enable signal to the clock. The different levels of the clock can actually enable state transitions. So we want these edge triggered state elements in our finite state machines for the reasons that we discussed earlier. So how do you build? Basically, a D flip-flop based register is very similar to another register that we did build using latches, except now we use D flip-flops. So this picture shows you 4 D flip-flops. So this is a 4-bit D flip-flop based register. And you can actually indicate it this way. This is one representation of it. This register stores 4 bits, and you can see that output is 4 bits also. This line represents 4 wires. That's what this 4 over here means with a slash on the wire. So you'll see this terminology a lot. And this is from your other book, Pat and Patel book, that basically shows essentially the same thing, but it shows the internals of the D flip-flop. And you can see how expensive this is, right? There, as I said, there are 8 gates, and there, how many transistors did we say over here? So 1 NAND gate is 4 transistors, right? So we have, how many transistors? Does anybody want to venture? So for one of these D flip-flops, you have 1, 2, 3, 4 NAND gates. Each of them has 4 transistors, that's 16, and then you have an inverter over here that is kind of hiding. That's 17, and then you duplicate that, that's 34. So each of them has 34 transistors. That's a lot, right? And we compare this to DRAM that has only 1 transistor. Okay. If I made the math wrong, please shout. It's okay. So nobody objects. Okay. Okay. So basically, now let's actually build a finite state machine based on what we've learned. We're not going to go into the details of the flip-flop anymore, but you will do this actually in your labs. We're going to get back to it in the later part of this lecture when we talk about Verilog and hardware description languages. We're going to figure out how to write this exact same thing in a hardware description language called Verilog. It's going to be very easy, actually. You don't need to worry about the internals, especially when you do the behavioral modeling. If you do the gate level modeling, as we will see later on, that's called structural modeling. You will need to know the structure. But if you do behavioral modeling, we're going to abstract it away, and you don't need to know the underlying implementation. But now you know why it's important to know the underlying implementation, right? How many gates could it be implemented with? Okay, so finite state machines, we said that next state is determined by the current state and the inputs. And there are actually 2 different types of finite state machines, depending on what the outputs depend on. In a Moore type of finite state machine, the output depends only on the current state. So output is really solely a function of the current state. And we will see this. And we will also see a Mealy type of finite state machine where the output depends on the current state as well as the inputs. Okay, so this is the way you design the machine actually. State, basically in the Moore type of machine, state directly indicates your output. In the other type of machine, just by looking at the state, you don't know the output value. You have to know the transition from the state. You have to know the input that goes into the state as well. And this has trade-offs. So let's take a look at one finite state machine example from your book. How many people have seen this? Okay, that's good. You're reading the book, I guess. Or maybe watched the lecture from the past. How many people are reading the book? Okay, that's great, yeah, okay. So basically, this is a supposedly smart traffic light controller, which is actually not so smart, as we will see, but it's trying to be smart, at least. Different from the traffic light controller that we've seen earlier. So in this particular case, we have two avenues, Avenue A, let's say, and then Avenue B, or Boulevard B, A and B, let's say. And the traffic light, there are 4 traffic lights, as you can see over here. And there are 2 inputs and 2 outputs to each traffic light. There are traffic sensors on Avenue A and Avenue B. And these traffic sensors are 1-bit inputs. And they respectively turn true when there's traffic on the corresponding avenue or corresponding road, let's say. And they're false when there's no traffic on the corresponding road. And there are 2 outputs. These are the lights, basically, LA and LB. And LA and LB are actually, I said 4 lights, but the lights on the Academic Avenue are the same, and the lights on the Bravado Avenue are the Boulevard are the same over here. And each of them have 3 states, as we have discussed. These are Swiss traffic lights as opposed to Texan traffic lights. There are 3 states, red, yellow, green. If you were living in Texas, it would be red and green. There would be no yellow. You could make an argument as to which one's better, but we're gonna not talk about that. State can change every 5 seconds. That's our assumption. But there's one but over here. Except if you have traffic on an avenue, and if the light is green, state doesn't change. You stay at green. So this is the smartness. Not so smart in one sense, because if you keep having traffic on one avenue, that avenue will stay green forever, right? So you will get denied service on the other avenue. So this is actually an interesting design thing. Whenever you're scheduling, you need to be careful about fairness and quality of service. So this traffic light doesn't satisfy fairness and quality of service requirements or definitions. It just says, if the light is green and there's traffic on this avenue, that avenue is prioritized over the other one. Live with it. So the people on the other avenue can go crazy. Fine, that's the traffic light that your book has. And this is basically a black box of the finite state machine that we have. You can see that all finite state machines have to have a reset state. That basically tells you where you start the system when it's reset, like when you power it up, for example. So don't ever forget the reset state, because the system is completely undefined if you don't know where to start from, basically, to begin with, right? So if I don't know how to start this machine, what is the reset state, then this machine can give me all kinds of junk output in the end, right? So this is critical. And there's a clock, as we said, because it's a synchronous finite state machine. And then there are 2 inputs. These are the traffic sensors. And then there are 2 outputs. These are the lights on the 2 different roads. Okay, I've already said all of these, I think. Yeah, now let's take a look at, let's construct this finite state machine diagram relatively quickly. We're going to construct the Moore finite state machine, but you could also easily construct a Mealy one. States are going to be circles. This is our state 0. The light on Avenue A is green. The light on Boulevard B is red. It just happens that way. And it happens that we're prioritizing that one in the beginning. Reset, whenever you reset, you go to that state. Transitions are basically arcs. So reset clearly causes some transition. Basically, you go into the state from an undefined point whenever you start. And then, you're not seeing that, but now you're seeing it. Whenever there's traffic on Avenue A and the light is green, you stay in state 0, as you can see. When there's no traffic on Avenue A, you go to state 1. And state 1 basically changes the light so that Avenue B can take over at some point. So you can see this is yellow and red now. And then going from state 1 to state 2 is unconditional. It doesn't matter what the lights are. At the next clock edge, you go to state 2, where the light on Avenue A becomes red and light on Avenue B becomes green. And then the same thing happens, basically. If traffic is there at the clock edge, at the next clock edge, you stay in state 2. Otherwise, if traffic is there on Boulevard B at the next clock edge, you stay on state 2. Otherwise, you transition to state 3. And then the transition from state 3 to state 0 is unconditional again, because this is an intermediate state where light B is yellow, as you can see. So this is a Moore type of finite state machine because states clearly indicate what the outputs are. Outputs are solely dependent on which state you're in. So outputs don't actually happen when you go from one state to another state based on some input. So if you look at this, and if the outputs are indicated inside the state circles over there, you can say that this is a Moore type of machine. Okay. Anything good? So based on the specification, you can design a finite state machine, and that's what we did basically. You can say specification is not great, so I'm going to enhance the specification in some way. Can we easily fix this problem? Because it's getting really annoying. Is it annoying for you guys? Yeah, I think so. I don't know how to easily fix it. I guess one option could be I could present from here, but okay, while you're doing that.
We need to go to.
Okay, okay, you need to.
People have to go to Zoom to share the screen again.
To share the screen? Okay, okay, let's do that. But can I quickly do that? I guess I don't know. Okay, maybe I'll take questions in the meantime. Any questions? So what we're going to do is basically we're going to build essentially the output logic, next state logic, as well as state register. Any questions? Any questions so far you have on NV? Yes, please. Other types of finite state machines, other than Moore and Mealy. I mean, there are other classifications like synchronous versus asynchronous, like we discussed last time, right? It requires a clock. Whereas the sequential lock finite state machine was an asynchronous finite state machine. So certainly, yes, there are other types of finite state machines, I would say. But in terms of how outputs are generated based on the dependence on the state versus state and inputs, it's just Moore and Mealy. Any other thoughts? Okay, good. Let's hope that this works. Thanks. Okay, this thing is also working, so I can see myself too. Okay, so now let's build the any other questions now that we've started questions? Okay, good. So we've switched to finite state machine, as you can see, right? Something that's controlling. You can also do that, right? So you can switch the finite state machine dynamically in a machine, in a real machine, and we will see that later on. Okay, let's build a finite state transition table. So we have the state transition table. Now let's actually turn this into a truth table, right? We know how to do that basically. We're going to decide the next state logic. Next state logic, as we said, is a function of the current state as well as the inputs. So based on what we built, this pictorial structure, if the current state is S0, and if there's no traffic on A, then the next state is S1, right? So basically, you can build this truth table relatively easily by just looking at things. And again, this is a butchered type of truth table. It's a compressed type of truth table, right? I don't have ones and zeros. I don't have every possible input value, but I'm going to expand to that in a little bit. And I also have don't cares, as you can see, right? I don't care what the traffic sensor on Avenue B is in state 0, because you can see that TB it doesn't determine anything, any transition from state 0. If the current state is at state 0 and there's traffic on Avenue A, it doesn't matter what traffic sensor on Avenue B is, the next state is still S0. So you can basically keep doing this. And then this is an unconditional transition, as you can see. If the current state is S1, it doesn't matter what the inputs are, the next state is always S2. At the clock edge, you change to that next state. Now let's encode these states. We're going to talk about encoding later on, but you can choose one encoding. This is one encoding. Since we have 4 states, we need 2 bits, right? That's the most compact encoding. And I assume these 2, well, your book assumed these 2 values. Now you can actually write states as 2 bits input, 2-bit values, let's say, that are stored in the state register. And basically, I just replaced S0 with 0, 0, S1 with 0, 1, S2 with 1, 0, and S3 with 1, 1 everywhere inside this table. Now we have a much nicer truth table. And now we can actually express this in terms of Boolean logic, right? S1 prime, this bit of the next state, is 1 now we're doing this sum of products form, is 1 only for these input values. Meaning S1 prime is 1 for if S1 is 0 and S0 is 1, and this doesn't matter. So you can actually write this. You can see that these are the implicants. Well, I wouldn't call that implicants. These are the values of the input variables that correspond to S1 prime being 1, right? S1 prime is 1 if this is true, or if this is true. S1 is 1, S0 is 0, and TB is 1, and it doesn't matter what this is. And this is a sum of products form, or somewhat reduced sum of products form, because we have don't cares over here of essentially this function S1 prime. And you can do the same thing for S0 prime. You can see that S0 prime is 1 only for these values of the truth table, this compressed truth table, if you will. And that corresponds to S1, S2, S0, and TA all being zeros, and S1 being 1, S0 being 0, and TB being 0. And these are the sum of products form, essentially, again, considering the don't cares. So everything we learned in combinational logic and logic simplification also applies here. You can simplify this, and this becomes S1 XOR S0, and the other one, unfortunately, you cannot simplify it further. So that's our next state logic, basically. Does that make sense? This is how you determine next state based on the current state and the inputs. Now let's take a look at the output table. We're going to do the same thing, essentially. Well, something similar, not exactly the same thing, of course. As we said, output, this is a Moore type of machine, so output is solely a function of the current state. That's why you don't see the inputs to the finite state machine on the left-hand side of this truth table again. And if the current state is S1, current state is 0, 0, S1, 0, S0, 0, then the LA is green and LB is red. So you can actually verify this. Now you need to encode the outputs, of course, because green and red doesn't mean anything. You cannot simplify that. So you need to encode green, yellow, and red. And again, there are three types of three outputs, so you need 2 bits to represent them in binary. And then you basically do the same thing. You start simplifying. LA1 is 1 if S1 is 1, as you can see, right? So we quickly did that simplification over here based on the uniting theorem, right? You remember uniting theorem says if for the onset of a function, in this case, the output is LA1, if an input changes and it covers all of the possible changes in binary in this particular case, it does, then you can eliminate it. So S0 can be eliminated. So LA1 is represented as 1. And LA0 is 1 only in this case. S1 is 0, S0 is 1. And this happens to be LB1 is 1 when S1 is 0. So it's S1 prime, as you can see. This again based on the uniting theorem. And then LB0 is expressed this way. So this is the output logic, as you can see. So each bit of the output is determined as a function of the bits of the state. Makes sense, right? Okay, so there's no magic, as you can see, right? Any finite state machine, you can reduce it to a truth table. Once you have the pictorial state transition table, and once that's correct and complete, you can reduce it to a truth table, and then you actually optimize the. You can actually express the next state logic and the output logic, which is what we did right now. Okay, let's take a look at the schematic right now. So this was our finite state machine general. Our state register is going to look like this. Basically, it's a 2-bit state register, and this is the current state on the right, clock, reset, and then this is the next state on the left, next state bits coming in on the left, and there will be a logic that determines next state bits, as we discussed. And this is the logic that determines the next state bits based on what we did earlier, right? For our traffic light, smart traffic light, I should say. Okay. So hopefully that's clear. And this is the output logic. Basic output logic is solely a function of S1 and S0. Inputs doesn't matter over here. For the next state logic, you can see that inputs TA and TB mattered, obviously. But because it's a Moore type of machine, the next state logic, so output logic is only dependent on the current state. Okay, no questions. We can move on. So this is something I'm not going to cover in detail, but this is good to think about. This is a timing diagram based on some inputs. We're going to cover more on the timing diagrams tomorrow. This is just to jog your thinking a little bit. So you're in this current state, and then inputs. No, something is happening over here. You can see that reset. reset basically resets the current state, right? Because reset is high, you reset the current state and you go into the state. And this happens to be actually a flip-flop with an asynchronous reset, because the reset takes effect almost immediately regardless of the clock edge. So we're going to talk about that when we talk about the Verilog lecture. So reset doesn't depend on the clock, basically. Whenever you reset the machine, doesn't depend on the clock. So this is not a completely synchronous system from that perspective, but we will talk about that when we talk about flip-flops in hardware description languages. And then you can see that you're in state 0 over here, and it happens that TA is 1, so you still stay in state 0 over here, and then TA becomes 0 right at the clock edge over here, so you transition to state 1 over here, and it takes some time. So transitions actually take some time based on the combinational logic delay. Because remember, there are two types of combination logic over here. The next state logic, what is the next state going to be? And what is the output going to be, output logic, right? And because there are non-zero delays that you have in these gates that, for example, the NAND gates earlier or AND gates, it takes some time to transition from state to state. So it takes some time for the outputs and the state to change. And that's what this delay is. And we're going to talk about that a lot when we talk about timing and verification. This is just to prepare you for that. And you can see that transition from state 1 to state 2 is unconditional. It doesn't matter what the inputs are. TB is 1, for example, it doesn't matter. You transition to S2. And then you can see that next state stays in S2 because TB is 1 while you're in S2. And then you transition to S3 when the TB becomes 0 at the next clock edge. It just happens to become 0 over there. Okay, and then there are some transition delays. So if you want to go through this in full, you should look at H&H chapter 3.4. It actually has this demonstration, but we will see in timing and verification. So this means that if you want to properly transition, if you want this to work correctly, your clock cycle should be long enough to accommodate the delay of the combination logic and the latching that we have, right? This is really critical. If your clock cycle is so short that the combination logic takes longer time to settle, to evaluate its outputs from the time inputs change, then you will not get a properly working system. That's the importance of timing. Your clock cycle should be long enough to accommodate the longest combinational logic delay that you have in your system. And we've actually seen that combination logic. So let's go back. So this is there are two combination logic. One is this. Your clock cycle should be long enough such that after TA and TB change and S1 and S2 start propagating, this delay over the circuitry settles. Basically, your clock cycle should accommodate the delay of the circuitry as well as this circuitry over here. If your clock cycle is too short over here, you will get the wrong output in a given state, right? Here, if your clock cycle is too short, you will change the state to a wrong state potentially, or you may not change the state because you didn't give enough time for the circuit to actually finish evaluation and get its output latched in the state register. Okay, now I introduced some timing into this, right? So far, we've been very logical, but timing is really important in these. Okay, so let's go over. We're going to see more of this. And we're going to see actually in timing and verification that it's really a sequential system that we're talking about. A sequential system, beginning of the clock cycle, ending of the clock cycle, there's some combination logic, and you have to accommodate the longest combination logic delay. If you cannot accommodate it, divide the work into multiple different, let's say, clock cycles. And we will see that when we talk about pipelining, for example, later on in the principles of design of microarchitecture. So I'm kind of getting ahead of myself, but all of this is actually will be building up to a microarchitecture that processes instructions. And that instruction processing can be done in one single clock cycle, as we will see. And we will see that that's very long clock cycle. So we're going to chop it into pieces such that your clock cycle can be shorter. But now you need to design a finite state machine that processes instructions in an appropriate manner in multiple clock cycles. So whatever we're going to see in a few lectures is going to build directly on top of what we're seeing right now. Okay, so state encoding. So we just assumed some state encoding. how do you encode the states? And then we just assume some output encoding. How do you encode the outputs? So basically, there are three common ways of encoding states with different trade-offs. I will not go into a lot of trade-offs over here, since this is not a, again, logic synthesis or design optimization course. But just to give you an idea, they're fully encoded, one-hot encoded, output encoded. Fully encoded also means binary encoded. So let's take a look at our Swiss traffic light again. You can see that we have 4 states over here, and this is a pictorial representation of it. Binary encoding, full encoding means that use the minimum possible number of bits. If you have 4 states in binary, minimum possible number of bits is log 2 to the 4, and that's basically 2, right? And then you can assign some encodings over here. This minimizes the number of flip-flops that you have clearly, but not necessarily the output logic or the next state logic. So that's the trade-off basically. You minimize the state elements, but now your combination logic may be bigger. So there's a trade-off over here, which is interesting. Of course, in the small circuit, it may not matter that much, but in large circuits, this may actually matter, especially in large circuits with many, many, many states. If you think about a processor today, it has millions of states, maybe even, actually even much larger than millions, an understatement, if you will. Okay, one-hot encoding, basically here, each bit encodes a different state. You use the number of states to number of bits to represent the state. So you have 4 bits basically in this particular case. And exactly 1 bit is hot or 1 for a given state. So you can see that 0001 represents 1 state, 0010 another state, 0100 another state, and 1000 another state. So this is nice because this is very easily automatable. It's the simplest design process. You know exactly which bit is set for a given state. Unfortunately, this maximizes the number of flip-flops, but as I said, it minimizes, it is actually very automatable as well as it minimizes the next state logic. So next state logic becomes much simpler right now. So there are trade-offs, as you can see. And the final one is output encoding. Here, outputs are directly accessible in the state encoding. For example, if here we have 3 outputs, right? That's the light color. We encode the state with 3 bits, where each bit represents a color. So you can see 001, bit 0 encodes the green, and bit 1 encodes yellow. This is 010, that's yellow. And bit 2 encodes red, that's 100. And then there's another state that has both yellow and red, and that's encoded as 110. So in this case, outputs are directly accessible from the state. And this works nicely for Moore machines, because in Moore machines, outputs depend only on the state, not on the inputs. Clearly, if outputs depend on the inputs, you cannot do that, right? You cannot encode the outputs inside the state encoding itself, right? Okay, so this is also good. This minimizes the output logic, but as I said, it has some limitations. So next state logic is another issue over here, which we're not going to discuss. So basically, it's the job of the designer to carefully choose an encoding scheme to optimize design under given constraints. Again, automated synthesis tools do some of this, but if the circuit is very, very large, as we will see later on, its designer actually is an important, let's say, participant in the process of optimization. Any questions? Okay, hopefully these are not too bad. So Moore versus Mealy machines, going back to Moore versus Mealy. Let's design a couple of things, again, based on your book. This is just a reminder, Moore output depends only on the current state, and Mealy output depends on the current state as well as the inputs. And your book has an example. How many people remember this example? The smiling snail? No one? Okay, some people, that's good. So basically you're designing, well, you're modeling, in this particular case, you're not designing the snail, you're modeling a snail's brain. And the snail happens to be a somewhat intelligent snail. It's able to interpret the bits or digits that it crawls over. And if it actually sees a sequence 1101, it basically smiles. Magic, right? Basically, you're modeling the snail's brain. How do you do that? You could do it with a Moore FSM or Mealy FSM. So basically, if someone gives you this problem of modeling, you design this as a state machine, right? The snail smiles only when it sees 1101 in a sequence, and otherwise it doesn't smile. So smile is an output. It's 1 only in this particular state where you reach after seeing 1101, right? And then after that, whatever you see brings you to the reset state. So you have to have a reset state, as you can see. And here we have 5 states. In the 5th state over here, you know that you have seen 1, 1, 0, 1 in sequence, and then this state directly corresponds to the output smile, and that's 1. Every other state, smile is 0, meaning the snail doesn't smile. And you can make sure that this works, and it works. Mealy FSM, on the other hand, looks like this. We didn't design this so far, but I want to introduce you to this one also. But basically here you have 4 states only. So it actually reduces the number of states, as you can see. But reset is here. You have not seen anything. Assume that. Nope. So if you've seen a 1, the output is 0. The smile is 0. So this is the input, this is the output, and you go to state 1. And state 1 basically says you have seen a 1. And you see another 1, the output is still 0. You go to state 2. And you see a 0, the output is still 0 because you have seen the sequence of 1, 1, 0 right now. And that's what the state means. And now if you see another 1, you go to this state and you output 1. So basically you can play tricks like this. You can actually combine different states over here because your output is now independent. Well, I shouldn't say independent, or partially dependent on the state, right? Partially dependent on the previous state you were in and the input that was applied to the previous state, right? So basically once you see 1, 1, 0, 1, you're at this state and your output is 1. And then you can basically keep emulating what it does. So I don't want to go through the details of this, the state machine, but you can see that there are some trade-offs over here with Mealy FSMs because the output is not solely a function of the states. You can actually reduce the number of states, but your output logic may become more complicated this way. But again, in big machines, this may matter. Okay. So we may ask you to design finite state machines, and actually you will do that in your labs especially, but who knows, maybe in the exam also. This is not a difficult procedure, as you've seen, right? With simple finite state machines, it's not that hard. You need to determine all possible states of the machine. You need to develop a state transition diagram. And this is generally done from a description of what should happen. And clearly, this should have everything, inputs, outputs for each state, as well as how to get from one state to another. And don't forget the reset. Reset is very important. And as I said over here, yeah, I don't know if I want to go through all of these over here, but I will mention that this is building an FSM is kind of like programming, right? Like what you've done over here in modeling the brain of the snail is kind of if the input sequence is 1, 1, 0, 1, you output a 1, right? You can actually write a program that does this relatively easily, except we're doing it as a sequence of states, not as a, let's say, program that you're used to. So it is not programming, basically. You're really designing a stateful system in the end. And as I said, as I just mentioned, gave an example of it as a sequential control flow, like a program with conditionals and go-tos. For example, if I'm in this state and if I've seen a digit 1, I should go to this state. Otherwise, I should go to this other state, for example, right? So basically, you can actually express a finite state machine as a program. It's not that hard. Yeah, I think I've said this. If then else construct is controlled by one or more inputs, and the outputs are controlled by the state or the inputs. Basically, in hardware, you typically have many such concurrent finite state machines, and we're going to see that again next week. One of the finite state machines may be decoding instructions. Another finite state machine may be controlling the execution of the instructions. Another finite state machine may be actually controlling what's happening in the accelerator over here. Another finite state machine may be controlling what's happening in the memory side. Another finite state machine may be controlling the SSD. So you actually have a bunch of finite state machines that interact with each other. And overall, it's actually a huge finite state machine that you can model. But you really normally build hierarchy of finite state machines when you build hardware, because clearly designing a single finite state machine for everything that goes on concurrently is very difficult, right? I mean, you can imagine, again, each of you as being finite state machines, and you're interacting with each of you who are different finite state machines over here also, right? You could try to model everybody together in this room as a single finite state machine. You would be probably plucking your hair by the time you're in the middle of that, or maybe 5 seconds into that. But it's a lot easier to actually describe each one of you as a different finite state machine that is interacting with others. Okay, any questions? Okay, so what is to come? Basically, we're going to see the finite state machine of this one. I didn't show you over here, but you can take a look. This is going to be, basically what we have done so far is build up the fundamental blocks, starting from the transistor, combinational logic, sequential logic, we're going to see all of these. Basically, you can see that there's some state element over here, register file. There's some memory over here, input output. There's a bunch of combination logic that we will see over here. This is going to be a finite state machine. We're going to design actually this LC3 processor that can process instructions from a small instruction set. And you're going to do something like that in your labs as well. And this is going to be the data path that we're going to see and build. You can see some of the elements that we've seen so far, multiplexers, for example. There's a decoder somewhere that's not shown over here. But we're going to use everything that we have used so far. You can actually see the tri-state buffers over here, right? And then there's a bus over here. And these tri-state buffers control what data value gets loaded onto the bus. Again, that's a teaser. We're not going to go into that right now. But I think this gives me a nice time to give you a 10-minute break. Does that sound good? Let's take an early break right now, and we'll be back in 10 minutes to start lecture 5B. What's up?
Busy these days, right?
Yes, I am. What's up? Yeah. If you did it 5 times over the entire lecture, it would have been okay. But Mhm. Okay, let's get started. So now that we know how to build combinational and sequential circuits and finite state machines, we'll see how to describe them in hardware languages, hardware description languages, and in particular Verilog. And you're going to use this a lot in your labs. And again, you will have exam questions related to this. You can actually easily see those exam questions. Hopefully they'll be easy. I think once you know a concept, it's relatively easy, right? The key is getting to that stage, that knowing the concepts. Okay, so this is what I intend to cover. Probably we're not going to finish all of it in the remaining time. We're going to start hardware description languages. We're going to look at how to implement combinational logic in them. We're going to implement we're going to see how we implement sequential logic in them. And we're going to basically implement the finite state machine, the smiling snail at the end. And if you don't get to it, you can look at the slides, and your book also has them. But basically, the Verilog, especially the Verilog part of this, constitutes a tutorial. We may not be able to cover it all, as I said. You need to look at it yourselves anyway for the labs. And people have gone to the labs this week, right? How many people have gone to the labs so far? Good. How many people have not gone to a lab yet? Yes, there are some tomorrow, so hopefully you'll go tomorrow. Don't ignore them, they're good. Okay, so as I said, as a teaser, you should be able to design a processor like this by the end of this course for sure, assuming you know the full specification, and you know the full specification of this in your book, for example. And again, you should be able to design a processor like this. And there are readings. I'll keep putting these. I've already discussed what readings are. If you're perfectly understanding everything in the lectures, truly you don't need to do any of the readings. You should really do the homeworks, I would say. But of course, readings provide additional material that could be very useful for understanding. For example, in digital building blocks, I say recommend it. It covers a lot of stuff that I don't cover, that we don't have time to cover. But I mean, it's interesting stuff. Like it talks about multipliers, right? How do you design a multiplier? We're not going to cover that. We don't have time for that. Could be useful for you. Okay, and just a reminder, we have extra credit assignments that are, let's say, freebies for you almost. Okay, so let's jump into hardware description language and Verilog. So I'm going to motivate this from a complexity perspective. So this is a processor that was the state of the art about 5 years ago. It had 1.75 billion transistors. That was a lot, basically. People were thinking, what happens when we get to 1 billion transistors? We're already way over 1 billion. And that's nothing. This is 2021. This thing has 16 billion transistors. And in 2022, this thing has 114 billion transistors. And you can actually have this as a consumer system. You need to pay a little bit to get it, but 114 billion is a lot, right? And there's a lot of stuff in it. You can see we're going to cover the principles of all of these things actually. So there's a lot of complexity in this basically. But then it doesn't end. You can actually increase the number of transistors. This is the Cerebras' wafer scale engine, this big. 1.2 trillion transistors and 2.6 trillion transistors. This is one of the biggest compute chips that we have today. And I actually went to Wikipedia to see what Wikipedia has to say about transistor counts. And as expected, Wikipedia told me that compute chips, they're interesting. They have lots of transistors. But if you look at memory chips, they have orders of magnitude more transistors or and other structures in them. So you can see that this is a flash memory. This is a single chip, 5.3 billion transistors in a three-dimensional stacked flash memory. That's much larger than the wafer scale chip. And this flash memory is not wafer scale. This flash memory is something like this, basically. Yeah, and you can see some of the things over here. It's actually also good to read it a little bit. For example, let's read this. In terms of computer systems that consist of numerous integrated circuits, basically these are bigger systems. The supercomputer with the highest transistor count as of 2016 is a Sunway Taihu Lite, which has for all CPU's nodes combined about 400 trillion transistors in the processing part, which is actually small because it's 2016. And the DRAM includes about 12 quadrillion transistors. That's quadrillion is 1,000 times a trillion. And that's about 97% of all the transistors. So you can see what's important here, right? So we're going to talk about memory toward the end of this course, but never lose that perspective. A lot of people lose the perspective, in my opinion, even in the cutting edge, that compute is important and they design these powerful compute processors. In the end, they're going to be bottlenecked by memory, as we will see. Okay, anyway, there are interesting things over here, basically. To compare, the smallest computer as of 2018, dwarfed by a grain of rice, has on the order of 100,000 transistors. So basically, there's a lot of complexity that goes into these systems. Transistor count is one metric for complexity. It may not be a great metric, but it's a good approximate metric that shows how complex the systems that we're building are today. There's also a lot of heterogeneity, as you can see, right? There are different kinds of cores, different kinds of memories. How do we deal with it? Basically, how do you design a system like this? And there are two multiple principles over here that we will see in this lecture. But you need to basically describe the hardware in some way. And this leads us to hardware description languages. Basically, we need to be able to specify the designs or describe the designs, complex designs. We need to be able to simulate their behavior so that we can verify them from a functional perspective. Is this logically correct or functionally correct? And also from a timing perspective. And timing is a lot harder than functional verification, as we will see tomorrow. And also, we want to make our lives easier. We should be able to synthesize the complex designs, meaning automatically design these complex designs, ideally all of them, or at least some portions of it, right? So we need hardware description languages for all these three different things. Because synthesis is actually nice because hopefully you verify the synthesizing program that actually gets from your language to the gates, a library of gates, as we will see. So hardware description languages, or HDLs, enable all of the above. These are languages specifically designed to describe hardware. They're not like any language that we have, programming language that we have, they're not perfect. They're designed by humans, but the goal is specifically to design hardware, describe hardware, as opposed to software programming language. And we will see why this is important for hardware. So there's similarly featured hardware description languages at different levels of abstraction. Verilog and VHDL are two popular ones. We're going to use Verilog in this course. It's actually quite popular. Versions of these are actually used by many companies internally. They change it. They add different programming language constructs in their designs. So what you're going to be doing is very similar to what people do when they design hardware, real hardware, let's say. But the pictures that I showed you basically are designed using versions of these hardware description languages. There are also a little bit higher level languages that we may talk about as well. But basically, if you learn one of these languages, it's really not hard to learn another. And if you're actually good at one of them, you can actually design hardware relatively quickly, and you will have some skills that are actually very sought after today. Because if you're good at them, you know actually how to optimize the hardware designs as well. Mapping between languages is typically mechanical because there's always a commonly used subset between them. We're not going to talk about those as much. So let's talk about what these hardware description languages are. There are two major well-known low-level hardware description languages. These are Verilog and, yeah, I'm not going to talk about all of these things. VHDL, they're both good. We'll use Verilog. Okay, I don't want to give you the history, but you can read the history. It's not that interesting. I mean, it's interesting, but it's not that interesting for the purpose of this course. I'm not going to ask you who developed Verilog, for example. I don't care. Right? That's not an interesting information that you should get out of this course. It's good, let's say, trivia question that you may answer, I don't know, in some online competition, but that's not the purpose of this course, right? You should be able to reason about how to use Verilog to actually design good hardware. Okay, so why specialized languages? Why don't we use Java or Python to describe hardware? Well, because those languages don't have some things that Verilog and VHDL have, which is really the hardware constructs that you actually express when you design hardware, like wires, gates, registers, flip-flops, clock, rising and falling edge that we've discussed. Basically, these specialized languages have specialized primitives that enable you to express or describe these elements, combinational and sequential logic elements that we have. You can certainly extend Python to have these, then it becomes a hardware description language also. Okay, and also this is one. You can express hardware better, and also you can express parallelism that's inherent in hardware. This is actually very important because hardware is inherently very parallel. As I said, you have lots of finite state machines, lots of things going on in a circuit. Everything is happening in parallel, actually. This is very different from software, if you think about it. Whenever you learn software, you basically have usually a sequential imperative language, and you basically go through statements, right? One thing happens after another. Hardware is nothing like that. Internally, it's completely parallel, and these hardware description languages need to enable you to express this parallelism that is inherent, and we will see how this is done in Verilog. And normal, at least general programming languages like Python, they don't have this sort of parallelism. I mean, you can have higher level constructs for parallelism like threading, etc., in many languages, but that's not the same kind of parallelism here we're talking about. We're talking about every single gate changing its output every single clock cycle, potentially, depending on inputs changing, right? Okay, and this could be millions of gates at the same time. It's not just a single statement that you write in Python, right? Okay, that said, basically, both of these properties enable ease of specification, simulation, and synthesis. So that said, people have actually tried a lot to write the specification of hardware using a programming language like C, for example. I don't think that anyone has tried with Python yet, maybe. Maybe they have tried it. I think they have actually tried it. But so you can actually do that, but then synthesis becomes very difficult because you describe hardware at a very high level, as we will see also. And the synthesis tools become very, very unoptimized because the state space that they need to search through is huge because you really have not described what's a wire. The synthesis tool needs to figure out what's a wire, for example. So there's a lot of potential over here actually for new techniques so that you can compile from Python or C down into gates and wires, but it's very difficult to do. And the circuits that usually end up that you see are very unoptimized. Okay, we may get back to this because there are intermediate level languages that you can use. Python and C may be very high level, but you may actually have a hardware customized language that can enable you to do this high level synthesis. Okay, so let's talk about hardware design using hardware description languages. So a key design principle to tame complexity that we have seen will be hierarchical design. Basically, if you look at the structure of a huge processor, you can design it using a hierarchy of modules. And you can see some of the modules over here: cores, caches, I don't know, accelerators, memory controllers. So these are basically different components. And each component may have hierarchy. You can see that there's a shared LT cache bank. We will see that. And then bank has subarrays, etc. And each subarray has some number of gates. And basically, these are the memories that you have seen earlier, similar to that. So you basically have predefined primitive gates, as we will see, and or, for example. And you build simple modules on top of those by instantiating those gates. For example, components like muxes, multiplexers, decoders, etc. Complex modules are built by combining and instantiating simple modules together, For example, a multiplier you can build by combining multiple of these modules, multiplexers, shifters, adders, right? And this hierarchy actually controls complexity. So the hierarchical design is really important. And this is very analogous to how you design software in some sense, because you don't design everything as a single huge blob, right? You actually start with some functions, and based on those functions, you build up to larger programs, and vice versa. You start from the top and go down. We will see that methodology over here as well. So complexity is huge, as we discussed, right? I'm not going to harp on it more, but this is going to be important, basically. And as we said, there are many different metrics today. It's not just how big your hardware is, it's also how much power does it consume, how much energy does it consume, how slow or fast it is, what is the latency. So basically, once you describe hardware, you need to actually go down to the next level to actually build it. And that step can be synthesized, as I said, and the synthesis tools need to be able to map what you describe to a library of gates that actually implement that function. And those library of gates can actually have many different types of adders, for example. And you need to somehow guide this tool to actually choose the right type of adder to maximize some metric. Okay, so as I said, there are multiple design methodologies, top-down and bottom-up. I alluded to it. But you can start with the top-level module and then identify sub-modules that are necessary to build the top-level module. Sub-modules, as you can see. And then you can subdivide the sub-modules until you come to the leaf cells. So this is top-down design. Your top-level module may be a processor, and then you decide what are the sub-level modules, decoder, L2 cache, L1 cache, I don't know, adder or ALU, etc. And then each sub-module consists of sub-modules, and then eventually you have leaf cells. Leaf cells are circuit components that cannot be further divided, let's say. These could be logic gates or primitive cell library elements that you depend on, or that the synthesis tool depends on. This makes sense, hopefully, right? In software, you do this also, right? You have some top-level module, and you divide it to different functions, and then functions get divided into smaller functions, and eventually you have some primitives. And you can also do bottom-up. Usually, you do both of these when you design hardware. You first identify the building blocks that are available to you, leaf cells. These could be, again, in a library. Somebody might have designed them for you, and they may have different properties. You build bigger modules using these building blocks, and these modules are then combined in higher level modules until you get to the top level module. We'll see simple examples of this. But in real life, usually you do both. You have some knowledge of the leaf cells that are available to you, and then you design up. But you also design down, and then you may identify some leaf cells that you really need, for example, and you add that to the library. So you usually do both in real life when you're designing a system. Any questions? I'm going through these relatively quickly because these are high-level concepts that are hopefully familiar to you in programming. How many people are familiar with these concepts? Top down, bottom up? Okay, good. Basically, these are applied to hardware right now. But now let's be a little bit specific. How do you define these modules in Verilog? This is really the main building block in Verilog. As I said, we're going to focus on Verilog. You need to define the name of the module. You need to define the inputs and outputs. These are from hardware thinking, you should think of this as direction of the ports, right? Input ports and output ports. And clearly you need to define that. You need to name them and then describe the functionality of the module. And this is going to be our module. It could be decoder, for example. Right? Let's take a look at an implementation of it. So in Verilog, it's like a programming language. You can see that you declare a module. It's an example module. It has A, B, C, and Y. A, B, C are inputs, Y is an output, and then that's the end of the module. And you put the circuit description here. Simple. Right? I already said all of these. So you need to declare the type. So you can actually, there are multiple ways of doing things, just like in other programming languages. You basically can define this module this way, or can define the module this way. Port and direction declaration can be combined. It's usually there's a coding style handbook that you get if you're working for a company and they tell you, do it this way, otherwise your code will never pass verification or something, right? So that's how it happens. So what if you have multi-bit input and output? You can define these are called buses, multi-bit input and output. You can define these using this array type of construct, range end to range start. So this is the number of bits is range end minus range start plus 1. These are several examples, basically. This is a 32-bit bus named A. It basically consists of these bits, each of these bits, A31. You can individually address each of them in your module, for example. You can take A31 and end it with A15, for example. These are two different bits. from the 32-bit input, and you're ANDing it in an AND gate. Right? Output, you can see that this is an 8-bit output over here, B15 to B8, and then B2 is the other 8 bits over here. And then there's a single signal. It's described this way. So it's basically a 32-bit value, as I said, the first one. Actually, it's preferred over this sort of definition, which resembles arrays. Yeah, there's always some syntactic issues in any language, and Verilog has its own syntactic idiosyncrasies that you'll need to deal with, unfortunately. But that's how it is. Again, these are languages designed by humans, so there will be inefficiencies in them. But it's the most important thing when you actually write programs is you should be consistent. You should either use 31-0 to refer to multi-bit signals or 0 through 31. If you mix them, then somebody who's reading your program gets confused. Okay, let's look at manipulating bits. You can basically, based on what we just said, you can manipulate bits. So you can see that there's a 16-bit long bus and there's an 8-bit short bus. And you can assign the short bus to be, to get the bits 12 through 5 of the long bus. Basically, this is really called bit slicing. You slice some part of the long bus and assign it to the short bus, 8-bit short bus. It's basically, in hardware terms, you have a 32-bit wire or 16-bit wire, and you're using 8 bits that are named 12 through 5, and you're basically assigning it to a name short bus, right? Okay, concatenating is easy also, as you can see. Y is a 4-bit thing over here, and it basically takes A2, A1, A0, A0. These 4 bits coming from A are concatenated. Well, actually 3 bits, but because A0 is duplicated while you're concatenating it, as you can see. Well, duplication, we've already shown an example of duplication over here, but this is a duplication example. You can assign X as 4 A0 bits concatenated with each other, or this is another way of saying the same thing. So this is a simpler way. 4 A0s are concatenated with each other and duplicated. Makes sense. You'll get used to it when you do these things. So it's case sensitive. Verilog is case sensitive. Yeah, fortunately or unfortunately, depends on what you're comfortable with. Names cannot start with numbers. So there are a bunch of syntactic rules. White space are ignored. You got to get used to them. I'm going through these relatively quickly, as you can see, because it could be boring, but it's good to know. So there are two, this is important. So this is actually, this has a lot of implications. There are two main styles of hardware description language implementation. It's not specific to language. It's really specific to how you describe hardware. You can describe the hardware at a structural level, meaning at the gate level. The module body contains the gate level description of the circuit. So you need to actually specify gates and wires, etc. This describes how modules are interconnected. And each module contains other modules, instances. And interconnections between those modules are explicitly specified, as we will see. It's a very low level description of hardware. That's why it's called gate level. So this describes a hierarchy of modules defined as gates. Behavioral, on the other hand, is a higher abstraction layer, as we will see also. The module body contains a functional description of the circuit, not necessarily gates. So I can do, for example, if then else. If then else doesn't really correspond to gates. It could correspond to muxes, but it could also correspond to something else, right? So you're not really describing the gates at this point. It's a functional description. So it can contain logical and mathematical operators, as we will see. As I said, level of abstraction is much higher. And as a result, there are many possible gate level realization of a behavioral description. So gate level or structural, if you describe hardware using gate level, you're actually dictating what gates should be used. Of course, a synthesis tool can optimize and change those things. Yes, that's true. But it's starting from a very low level description. And the assumption is that these are the gates. Whereas behavioral, there is no description of gates. You say, for example, if then else, right? And then the synthesis tool can do many, many different things. If then else. It could implement it using tri-state buffers. It could implement it using muxes. It could implement it using something else. So there are many practical designs actually use a combination of both, because both of these can be synthesizable. Depending on what you're trying to do, sometimes you may want to describe something at the structural gate level, especially if you really want to optimize some circuit. Sometimes maybe you don't care how this circuit over here is. It's not on the critical path, as we will see the term critical path later on. You basically say, I'm going to describe this behaviorally, and hopefully the synthesis tool will deal with it nicely. Okay, so now let's see examples of this. Let's see the structural gate level hardware description language. So this is going to look like gate level, as you can see. We're down at the wire level. So this is our top-level module. Top-level module consists of two sub-modules called small. And you can see that top-level module has three inputs, A, C, cell, and then one output, Y. And then you can see that there are two identical small modules, first and second, connected to each other, and you specify the wires. Yeah, I already said this. Let's take a look at the Verilog definitions of this. So top looks like this. A, C, cell are inputs, Y is output, and then you specify the wire that's internal. So this is a very low-level description, as you can see. You need to specify what wires are. And small, there should be a description of small also, and you can see that it's like this. And you can see the naming, and then you can see the small over here, and the wire, I already said this. So basically, how do you actually describe the top-level module as a function of the small modules? Basically, you instantiate the small ones. You say small I first, because that's the name of the module. And you can say that basically the input A of the small module is connected to the input A coming from the top-level module. Input B is connected to the cell coming from the top-level module. And output Y of the small module is connected to wire N1. As you can see, that's the case. Basically, every wire needs to be named. And then the second module, input A of the second module is connected to N1, which is the output of the first module. And input B is connected to C, which is another input of the top-level module. And output Y of the small module is connected to output Y of the top-level module. Okay, it's so simple, basically, right? And then there should be some description of small, as we will see later on. It could be anything over there. It could be another module also, description of the small. It could be another level of hierarchy. So, okay, there are different ways of doing things, as we said. This is the short form. Here, you don't specify explicitly which input is connected to which wire over here or input or over here, and which output is connected to what. You basically rely on the ordering. The way the ordering is done in the function definition or module definition over here, ABY. So pin order, pins are basically these things, A, B, phi. It's very important. If you mess this up, if you reorder, for example, if you say cell A and 1, this is not going to work. Well, I guess it depends on what's inside there, actually. But you cannot guarantee that it works, because that means that cell and A should be, yeah, basically you need to have a commutative function, right, for that to work. Okay, yeah, this is a safer choice, basically, any pin order. And that's what I would recommend. Short form is not good practice, as it reduces code maintainability, and it's very prone to errors. I think these are some common sense programming principles also. Okay, let's do another example. So we have some basic logic gates that are predefined primitives, and we will see some of them. These are instantiated like modules, except they're predefined in Verilog. So they do not need a module definition. You don't need to define them. For example, an AND gate. You don't need to define an AND gate in Verilog. These are basically primitive functions in Verilog that helps describe hardware. So this is a multiplexer, as you can see. It's a 2-input multiplexer that you've seen, and by this time you should love this thing. It's beautiful. It's a selector, right? And you can see that, I mean, this is what you've seen earlier. Based on the select input, you either choose D0 or D1 as the Y output. And this is how you describe, basically. Mux2, that's the name of our module, inputs D0, D1, SY, they're all 1-bit inputs in this particular case. And then we define the wires, internal wires, not S, which is not shown in this picture. It's basically the inverted value of S, and then Y1 and Y2. And then basically what you do is you implement the NOT gate, which is, you don't implement the NOT gate, you instantiate the NOT gate, which is already in Verilog as a primitive, and output is on the left, as you can see over here, input is on the right. And then you instantiate an AND gate that takes NOT S and S as input, D0 as the other input, and then Y1 as output. That's basically instantiating, describing this gate over here. And then you instantiate the AND gate, the second AND gate, which describes this gate over here. And then you instantiate the OR gate, which describes this gate over here. And then you connect the output of the OR gate Y to the output of Mux2 Y over here. So this is basically our Mux multiplexer. It's very simple, as you can see. And you can see the level of abstraction is at the gate level. Clearly, we've defined gates over here. We didn't say if S is 1, Y is equal to D1. And if S is 0, otherwise Y is equal to D0. We did not say that. That would be the behavioral version of the Mux. Well, a behavioral version of the Mux, because there could be multiple behavioral versions of the Mux. You can use case statements, for example, switch case statements, as we will see. Does that make sense? Okay, good. So let's talk about behavioral. I think I've given you one example. So now we're going to raise the abstraction level. This is just some module, basically. It's doing something, as you can see. But this is now behavioral. There's no gates here. There's no and, not. They're logical functions, though. In this particular case, for example, y is equal to not A and not B and not C, or A. You can read the rest, basically. There are a bunch of logical functions over here. These are bitwise logical functions in this particular case. So it's behavioral because we don't explicitly specify gates over here. It's a low-level behavioral thing. We'll see higher-level behavioral descriptions. But this could easily be translated to gates, as you can see, right? You take these behavioral specifications and with minimal effort, translate them into not, and or gates. And implicitly, we're assuming that there's some precedence order of evaluation over here, like many languages have. So not takes precedent over and takes precedence over or. Makes sense, right? As a result, this is what you get. You have three input AND gates, and then one 3-input OR gate, and that's the implementation, with one implementation of this behavioral description. Okay? Hopefully that's simple. Okay. Now let's look at more interesting examples. Basically, you could do bitwise operators. These were bitwise operators, actually. You could have bitwise AND, bitwise OR, bitwise XOR. This is bitwise XOR, it's nice. Bitwise NAND, bitwise NOR. That's good. And then you can actually, these are actually, now you can see that these are 4 bits. Each bit is operated using bitwise operations over here. And this is a schematic view. Again, you can convince yourself that they look nice or they look correct. Okay, let's do other things. So this is a reduction operator that could be useful. Basically, instead of, if you want to AND a bunch of values, this is an 8-input AND gate, y equals AND of every single bit of A. Instead of that, you can basically use AND A. So y, a single input, single output, single bit output is the AND of an 8-bit value. Here you AND all of these bits. You reduce basically, you reduce the input value using the AND function, and that AND function happens to be an 8-input AND function in this particular case. So now you can see that this is not a gate level description. Gate level description would be something else, right? This is completely, now we're going higher level, right? Okay, but this is one implementation of that reduction operator. It's an 8-input AND gate, but other implementations could be multiple 2-input AND gates, right? It's a hierarchy of AND gates. Okay, let's take a look at now higher level abstraction. So this is how you implement a MUX in behavioral Verilog. You have 2 4-bit inputs, one select input, single bit, and one 4-bit output. And basically, yes, this is one way of doing it. If S is 1, then Y is equal to D1, otherwise Y is equal to D0. This is perfectly fine behavioral Verilog, but this is another way of doing behavioral Verilog. Y is equal to S question mark D1 or D0, or colon D0. If S is 1, Y is assigned D1. If S is 0, Y is assigned D0. Makes sense, right? You know about this ternary operator? Okay, good. If you don't, you'll get used to it. It's not that hard, basically. Okay, so this is called a ternary operator because it operates on 3 inputs, as you can see, S, D1, and D0, and that's what we need for a MUX. But again, this is not gate level. The gate level implementation can be completely different. We're not talking about ANDs, NOTs, ORs over here. And this is potentially one way of describing it, right, in hardware. So this is the MUX multiplexer. You've seen this picture in some way. Okay, let's do something more complex. So basically, now we have a hierarchy of, let's say, ternary assignments, which are essentially multiplexers or selectors, as we will see. You basically have four input data values, four 4-bit data values, one as input, one 2-bit select value, and one 4-bit output value. And if S1 is 1, you basically select this one. So a Y is assigned to this if S1 is 1, otherwise it's assigned to this. And this thing is assigned to D3 if S0 is 1, otherwise it's assigned to D2. And this other thing is assigned to D1 if S0 is 1, otherwise it's assigned to D0. So you can see that this is a hierarchy of selectors or muxes, multiplexers, and potentially this may be a more readable form, depending on what you prefer. But once you start reading ternary like ternary assignments, it's not that difficult to read the first one also. So, okay, that makes sense, right? We're going to see that. This is a 4-input mux, basically, right? There's a 4-input mux, which is kind of described as a hierarchy of three 2-input muxes. But there are other ways of defining it. This is another way of doing the same thing, right? Basically, you assign y. If s is equal to 1, 1, it's D3. Otherwise, if s equal to 1, 0, it equals D2. Otherwise, if s is equal to 0, 1, it equals D1. Otherwise, which there's only one case left, it's equal to D0. So basically, it's a cascaded assignment using ternary operators. And this, it's the same as if, else, if, else, if, else. That was those were more otherwises, right? Okay, so these are simple, hopefully. So, but you can see that these are behavioral descriptions. There are different ways of describing the same 4-input mux behaviorally. And I should have put a picture of the 4-input mux here, but it's not there. And here, again, we assume some precedence in the operators, as you can see. We don't have full parentheses to specify everything. We assume precedence. So precedence is important. This is highest and lowest. It's kind of like C, but of course, C doesn't have all of these operators. But you can see some of the operators over here that exist in Verilog. This is arithmetic shift. There are comparison operators, as you see, equal operators, and NAND, etc. Lowest is ternary operator. That's what we used over here. So the lowest priority is ternary operator. That's why this works. And the highest priority is not, as we kind of alluded to earlier. I mean, of course, it's not great to it's not great to always rely on precedence, because someone who's just starting may not be able to understand the precedence of operators. But over time, you get used to it. If you've done this 1,000 times, this is like a piece of cake, right? You just remember it. So how do you express numbers? Let's talk about that also, because it's important. Clearly, you need to express numbers. This is an 8-bit value. Basically, n specifies how many bits. That large B specifies, well, I should probably do this. Yeah. Yeah, express how many bits will be used to store the value. B is the base. In this particular case, small b is binary. And then it could be hexadecimal, it could be decimal, it could be octal. And then XX is a number. In this case, it's 8 bits. So, and in binary, you require 8 zeros or ones. Okay, you need to express the value in the base that you specified in. And you can also have invalid and floating values, as we will see. This is important to implement some constructs that we talked about, right? Especially floating construct. But invalid is also good to have. Underscore can be used to improve readability. Okay, there are a lot of interesting things here. Okay, these are some example numbers. I'm not going to go through this, but you can see different bases, etc. Now you're going to use these in your labs. So remember the floating signals. Let's take a look at them. Floating signal is a single signal that's not driven by any circuit. This is also called open circuit floating wire, also known as high impedance, high Z tri-stated signal. You've seen examples of this. This is the tri-state buffer that you saw. Well, one example that you saw. Basically, this is a 4-bit tri-state buffer. If enable is, Y is assigned to A, if enable is true, otherwise it's assigned to a 4-bit Z value, floating value, if enable is false. And that's how you actually enable floating signals. And that's how you implement the tri-state functionality, if you will. This is one example functionality. And as we discussed in the last lecture, Z is a valid signal because you don't, sometimes you may not want to connect one wire to another. And we've seen that in tri-state buffer, if you remember. Essentially, this is the tri-state buffer. This is the 1-bit version of the tri-state buffer. And we discussed this. This is exactly what we saw earlier in the combination logic lecture. And again, remember what we used it for. I'll give you pictorially. We'll see this in LC3 design later on. You have a common shared bus between two components, and only one component can put a value onto it. And if you want to do that, one way of implementing this is using tri-state buffers. You set this, if the CPU is transmitting something, then the tri-state buffer over here is enabled, the tri-state buffer over here is disabled, and the CPU can get this wire coming out of the CPU gets connected to this shared bus and gets distributed over the system to other components that may be needing that value, for example, right? And this is the example from your book that shows something similar. Okay, so now you know how to implement tri-state buffers in behavioral. So I should go back over here. This is behavioral design again in Verilog. Okay, so there's a sophisticated truth table for AND gates with Z and X values, and you can convince yourself that this is true. Basically, an AND gate, whenever any of the inputs is Z or X, the output is defined unless the other input is 0. That's basically the definition of an AND gate. You can convince yourself of that. Make sense? So Z means floating, X means invalid. In either case, the 0 input dominates actually. Because if one input as an AND gate is 0, if that's a correct AND gate, you'll get 0 at the end. Right? Otherwise, if any input is any of the inputs is 0 or X and the other input is 1, then you get invalid because you don't know the outcome. Okay, recall this X should not be confused, unfortunately, with the don't cares, even though a correspondence can be made. If you remember the simplified priority circuit, we had requesters with priority levels, and then we have a grant signal for each requester. So we had a 4-bit priority circuit. If, for example, A3 is requesting some bus, it's granted regardless of whatever the other requesters are requesting or not. So A3 has a complete priority over others, and we actually reduced that table using, let's say, don't care. So this other X that we use over here is don't care. It's different from invalid. So this means that it's not invalid. I mean, at some sense, you can think of that don't care as invalid, but it's good to actually separate the concepts. So this is here just to make sure that you don't confuse these two things. Okay, any questions? I've gone through a lot of syntax and some implementation. Now let's talk about what happens to this hardware description language code. So there are two things that is going to happen and that you're going to also experience in your labs. Synthesis or hardware synthesis, and the second is simulation. And both of these are very useful. So synthesis means there are tools that map, synthesize the hardware description language code to low-level cell libraries. In the end, what you get is a netlist describing gates and wires. So you describe hardware, you put it into a tool, and that magically tool gives you a set of gates and wires. Clearly, a structural Verilog helps us more easily, right? And the tool can perform many optimizations, logic minimization, logic simplification, for example, figuring out which gate is better to implement this function with, etc. But they cannot guarantee a solution is optimal, unfortunately, because especially with large designs. If the design is very large, optimality guarantee is very difficult. Even if you're considering one metric, minimality, for example, of the circuit. So these tools are not perfect, basically. People have been trying to design these tools to be perfect, but unfortunately, we're not there yet. And the main reason is basically, there's a lot of placement and routing that you need to do. In fact, this is a very computationally expensive problem. And more recently, I believe Google had a paper on using reinforcement learning to do this placement of wires and routing of wires. And they basically show that this reinforcement learning-based tool outperforms other tools that use heuristics to optimize the placement and routing. So there's actually a lot of effort that is going into these tools today, and people are more and more using machine learning algorithms, even though those algorithms are also not perfect yet. So basically, you need to describe your circuit in a nice to synthesize way. There are some constructs that are not easy to synthesize or not synthesizable. You'll see that later on. But this is really the most common way of digital design these days. You normally describe your circuit, and then you feed it into a tool, and then that tool gives you output. If you do not like that output, you go and optimize. That's how people do today. There are some really timing critical paths of a circuit. For example, that the tool may not be able to meet the timing requirement. You want to clock your processor at, I don't know, 30 gigahertz, right? At 30 gigahertz, you want this combination logic to be so optimized that it should fit that clock cycle. And you don't want to change your design to break the cycles, break that operation to multiple clock cycles. So what you do is basically, hopefully the tool will meet that timing. If the tool cannot meet that timing, then you go hand optimize. And if you're a really good designer, you may be able to meet that timing. If you're not a really good designer, the tool may be better than you, basically. But the tools are very useful. Tools are actually very useful for very good designers as well. Okay, so we can talk a lot about synthesis. There's actually a lot of interesting stuff, but we don't have time for that. So simulation is the other thing that you do with hardware description languages. Basically, simulation is you describe your hardware, and then you apply inputs to it, and then you look at what happens. So this is good for verification of your circuit from a functional perspective, as well as timing perspective, without actually building the circuit, right? So you basically simulate what happens. This is very similar to simulating your program, right? You wrote some program, you apply some inputs to it, or testing your program, I should say. You apply some inputs to it, and you look at the outputs, and you see if the output is correct based on that. Here, you can actually see more, and we will see that. Simulators can work on structural and behavioral HDL. And simulation is really essential for functional and timing verification, and you will do a lot of this in your labs to make sure your designs are working, essentially. So let's take a look at this example. This is a behavior Verilog. This is a synthesis of it. I mean, we've seen this already exactly, but simulation we have not seen. Simulation is basically, you can see that there are 3 inputs, A, B, C, and 1 output. You have a visual interface that shows how the waveforms change. So A, B, C, you apply inputs 1, 1, 1, and this is how Y changes over time. So you will see these diagrams a lot, so I'm not going to talk about it. But basically, you can observe how each of these signals change and how potentially internal signals also change, right? And then you can actually verify that the circuit is what you want. This is an important paragraph from your book. I'll just read it, I think. One of the most common mistakes, it's important, that's why I want to read this. One of the most common mistakes for beginners is to think of hardware description language as a computer program rather than a shorthand for describing digital hardware. If you do not know approximately what hardware your HDL should synthesize into, you probably won't like what you get. You might create far more hardware than is necessary, or you might write code that simulates correctly but cannot be implemented in hardware. Instead, think of your system in terms of blocks of combinational logic, registers, and finite state machines. Sketch these blocks on paper and show how they're connected before you start writing code. So maybe this is too early for you to really understand the implications of it, but basically, if you treat this as a program, you will actually write something that's not synthesizable potentially, or that is synthesizable but leads to huge amounts of hardware, a lot of inefficiency. So if you don't think from a hardware perspective how these things are going to be laid out at a module level, then you may actually have a synthesis result that's not good. That's what this is saying, basically. You need to know what you're doing, what your end goal is, and how hardware is actually eventually designed. So this may actually be, this is something that you may learn better with experience, but it's true. Okay, so what we've seen so far, we've actually done a lot of Verilog, structural, behavioral, simple logic, multiplexer, constants, etc., tri-states, but there's more. Now let's jump into more, unless someone shouts and says something about the prior slides. Everything's good? Okay, I mean, some of these are relatively easy since you know programming, but again, this is different from programming. So we can write Verilog code in many different ways. Let's see how we can actually do this at different levels of abstraction. Again, we're going to stay simple. You can have a very low level of abstraction that has poor readability in general, but this automates, this eases the automated optimization synthesis, especially for low level tools. Or you can have a high level abstraction. This is great for readability, and usually it leads to more difficult optimization because it creates a huge search space for low level tools to optimize. So let's take a look at the simple example of comparing two numbers, right? You can define your own gates as new modules, and we will use our gates to show how you can implement a 4-bit equality checker or comparator in two different ways. So let's define two gates. One is a 2-input XNOR gate. This is an XNOR, as you can see, and again, this is behavioral. But we're actually using the behavioral description of this gate, and then it's a 2-input AND gate. We don't have to use it clearly because Verilog already has these as gates, but we're going to make a point over here. Remember, we actually looked at this. This is from the combinational logic lecture. This is our equality checker. It's comparing whether two n-input values are exactly the same. A and B, if they're equal is 1, otherwise equal is 0, and this is a bitwise comparison. And you can see the XNOR gates over here, and outputs of the 4 XNOR gates that do bitwise comparisons of AI are ANDed or reduced using the AND function to produce the equal output. This is one way of doing it. Basically, this gate level description is instantiated using the XNOR gates, except AND gate is not a 4-input AND gate, it's 3 2-input AND gates. So it's a hierarchy of AND gates, right? So clearly, this is one way of doing it. It looks like a mess, right? And clearly, it's not readable. So, okay, you can do other things like you can do this. You can basically simplify it. You can actually change the ends over here, make them behavioral. That's good. Now you can have a 4-input and behavioral end function. That's good. And you can actually do the reduction operator, right? Which is essentially reduction, as we said. So now this end is optimized. Now, or XOR is this whole thing over here is essentially this. C is equal to, XOR B. And that's one way of writing it. Clear, this is still a pain to read. Not as much of a pain as this one, clearly. Also, naming your functions would be nice also, right? Okay. Well, this is better, probably. This is a really short version, right? Equal gets 1 if A is equal to B, otherwise it gets 0, right? And this is still synthesizable. This is nice because you can actually imagine a search tool, a synthesis tool that goes through and synthesizes. And it exists. Okay, so basically, you can write more reusable code. Basically, you can write better code or worse code. That's the whole point over here. But you can also write parameterizable code. You don't want to hard code the input widths, and you can do that in Verilog, basically. What if you need to compare different bit width numbers and you want to define a module to be to take an input as the take the bit width as the input? Clearly, you don't want to write modules for each of these. So we have parameterized modules in Verilog for this. For example, this is a true input mux, and the data inputs can be of width that's specified when you instantiate the mux. If you don't specify anything, it's going to be 8-bit data inputs. That's what this says, parameter width equals 8. So, but you can change it, as we will see in a little bit. And this is the mux, basically, as you've seen. We've already seen this mux, right? So you can set the parameters to different values when instantiating the module. Let's take a look at this example. This is the definition that I showed you earlier. And this is basically a true input 8-bit mux. Data inputs are 8 bits. Because I didn't change the parameter. The parameter width equals 8 is the default parameter value. But now, this is how you instantiate. It's not the greatest syntax in the world, as you can see, but yeah, syntax is never great. This is a 12-bit data input mux. Now we actually overwrote the default parameter. Or another way of specifying it like this, even worse syntax, let's say. But again, these languages were created in the 1980s, right? And syntactic improvements have become better over time, but it's never perfect. Okay, what about timing? Actually, you can actually define timing relations in Verilog, but the purpose is for simulation. It's not, basically, you cannot dictate the timing of some logic. You use these timings for simulation, and we will see this in the next lecture when we talk about verification of what you design. These cannot be synthesized. Basically, you cannot say this AND gate takes 5 seconds and that'll be implemented. 5 seconds, of course, is high, but I just made it up, right? Because that really depends on the library, logic library. It's not what you say. Okay, I can imagine a 40 gigahertz clock, and I can write them Verilog, but can it be implemented? Of course not, right? But you can use these timing relations to model the delay so that you can simulate. In the simulation, you can see, oh, if my AND gate takes 150 picoseconds, this is when the result will be available. And this is when the output of this combinational logic block will be available. So you can actually simulate and see your critical path, for example. So this is very useful. So this is, for example, timing relationships. This you invert the output after 5 nanoseconds, and your output is okay. I messed it up basically. So you need to define a time scale over here, and you basically these are to the simulator. You indicate that the output is inverted after 5 nanoseconds, and then the output gets assigned after 9 nanoseconds, right? And in the simulation, you will be able to see that. So this is actually useful to model some things and maybe guess your critical path, but more on this soon. So there are a bunch of good practices. Being consistent is good, like any other programming language. These are good software engineering principles, I would say. Use most significant bit to least significant bit ordering of buses, this one as opposed to this one. One module per file is useful in general because it makes designing things easier. And yeah, module name that matches the file name is good. And always keep in mind, most importantly, if you disregard every single rule, you can still design hardware that could be hardware description that could be read only by you, probably. But you can still describe hardware in a good way if you really know that Verilog actually describes hardware. Right? You can be a great designer that actually accomplishes very tight timing parameters, for example, but the code may not be read by you. It may not be able to be read by anyone but you, let's say. Hopefully you'll be able to read your code. Okay, so let's see. No, this is a great time to stop. Basically, what we've seen is an overview of Verilog, structural and behavior of Verilog, combination logic circuits. In the next lecture, we're going to start with sequential logic, and then we're going to conclude this, and hopefully we'll start timing and verification. And that's going to be tomorrow. So have a good day. See you tomorrow.